Hello everyone, it's Color from 19, and today's day 3 on my challenge journey. I took a break during the whole weekend, and the weekend, even though I didn't record my videos, I just did some programming assignments from this course, as I always do. And let's recap first, and then start studying. So in the weekend, I did a logistic regression with a neural network, a programming assignment. And this assignment is quite well designed to follow each steps with enough description. So at the first step, I imported some packages to proceed this assignment. This image is quite useful to understand how the neural network, the simple neural network works. So in this case, as we already learned in computation graph, we calculate the computation graph from the input feature, which is the uh, originally we have three channels about for each R and G and B, and we can vectorize it in as a column vector, and we can use the input as an input feature. Then we map the each of components in vector to some variables, and with um, mapped weight and bias, we can calculate the linear function, and we activated it a sigmoid function. Then we can um, determine that whether it is cat or not by the probability prediction from this activation function. This image tells us that actually we can get a loss by the prediction and actual y by comparing it, and the log function is used for that. And the overall cost function is always known is the sum of all loss function, and then we average it. So it is cost. So when we model a neural network, there's of several steps, several sub-steps. Instead of putting all the steps into one function, it can be a good way to modularize the sub-steps into other function. So here we made a sigmoid function to calculate the sigmoid from input parameter z, and there's also function to initialize parameters with zeros. You see that w is a vector and b is a real number because it can broadcast to match with the dimension of the target operation matrix. So we don't need to set it as a matrix. It's enough just to set it as a real number. And as already see, in this graph, we need to calculate the forward propagation and backward propagation. And we read that in the propagate function. So here we have the labor number, I mean the number of labels, training examples, which is M. We have jet using the linear function. And we use sigmoid module to activate it. And we calculate the cost function here using these equation. What we need to know that because we already learned in the vectorization concept, when we do like these kind of semantic mass operation, it actually operation between the vectors and vectors. Uh, it seems like just we are doing it for for a number, but actually it did for whole vector. So we need to match the dimension of the dot product. In this case, y is a row vector, and np log is also row vector. So we need to transpose it to the dot product between of them. After the forward propagation, we need to do backward propagation to get derivatives. And here is djet. And follow the formulas. And we did np sum to cumulative each derivatives of in dwi. So that's enough. And this 4.4 section is really crucial section in this assignment. The reason that we do a backward propagation is for to optimize um, the learned parameters, to minimize cost. So inside of optimized function, first we do propagate, and from the propagate we can get the dw and db for each steps. And by given learning rates, we update w and b, which is the actual parameter of our equation. And we can keep iterated until this input iteration number, which is 100 in this example. And finally, we need to predict. After the optimize, we get W and B, and using it, we can predict predict Y hat from specific X. We can compare it, and then determine that whether it's a cat or not by our algorithm. In here, we use just simple condition. When the Y hat, the prediction is bigger than 0.5, it is a cat. Um, Otherwise, it is a not cat. So if we merge all the function to a model, we can make this kind of models. Yeah, pretty nice. So this is the end of second week in your network course, and now it's time to learn third week.
Welcome back. In this week, you learned to implement a neural network. Before diving into the technical details, I wanted in this video to give you a quick overview of what you'll be seeing in this week's videos. So if you don't follow all the details of this video, don't worry about it. We'll delve into technical details in the next few videos. For now, let's give a quick overview of how you implement a neural network. Last week, we had talked about logistic regression. And we saw how this model corresponds to the following computation graph, where you did put the feature x and parameters w and b that allows you to compute c, which is then used to compute a, and we were using a interchangeably with this output y hat, and then you can compute the loss function L. A neural network looks like this, and as I'd already previously alluded, you can form a neural network by stacking together a lot of little sigmoid units. Whereas previously, this node corresponds to two steps of calculations. The first is to compute the z value, second is to compute this a value. In this neural network, this stack of nodes will correspond to a z-like calculation like this, as well as an a-like calculation like that. Respond to another C and another A like calculation. So the notation, which we'll introduce later, will look like this. First, we'll input the features x together with some parameters w and b, and this will allow you to compute C1. So new notation that we'll introduce is that we'll use superscript square bracket 1 to refer to quantities associated with this stack of nodes. It's called a layer. And then later we'll use superscript square bracket 2 to refer to quantities associated with that already. That's called another layer of the neural network. And the square brackets, like we have here, are not to be confused with the superscript round brackets, which we use to refer to individual training examples. So whereas x superscript round bracket I refer to the ith training example, superscript square bracket 1 and 2 refer to these different layers, layer 1 and layer 2 in this network. But so going on, after computing Z1, similar to logistic regression, there'll be a computation to compute A1, and that's just a sigmoid of Z1. And then you compute Z2 using another sort of linear equation, and then compute A2. And A2 is the final output of the neural network and will also be used interchangeably with y hat. So I know that was a lot of details, but the key intuition to take away is that whereas for logistic regression, we had this C followed by A calculation, in this neural network here, we just do it multiple times. It's C followed by A calculation, and a C followed by an A calculation, and then you finally compute the loss at the end. And you remember that for logistic regression, we had this backward calculation in order to compute derivatives, right? So computing dA, dz, and so on. So in the same way, a neural network will end up doing a backward calculation that looks like this, in which you end up computing dA2, dz2, that allows you to compute dw2, dp2, and so on in this sort of right to left. So that gives you a quick overview of what a neural network looks like. It's basically taking a logistic regression and repeating it twice. I know there was a lot of new notation, a lot of details. Don't worry about it. If you didn't follow everything, we'll go into the details more slowly in these videos. So let's go on to the next video and start to talk about the neural network representation. See me draw a few pictures of your neural networks. In this video, we'll talk about exactly what those pictures mean. So in other words, exactly what those neural networks drawing represent. And we'll start with focusing on the case of neural networks with what's called a single hidden layer. Here's a picture of a neural net. Let's give different parts of these pictures some names. We have the input features x1, x2, x3 stacked up vertically, and this is called the input layer of the neural network. So maybe not surprisingly, this contains the inputs to the neural network. Then there's another layer of circles, and this is called a hidden layer of the neural network. I'll come back in a second to say what the word hidden means. But the final layer here is formed by, in this case, just one node, and this single node layer is called the output layer and is responsible for generating the predicted value y hat. In a neural network that you train with supervised learning, the training set contains values of the inputs x as well as the target outputs y. So the term hidden layer refers to the fact that in the training set, the true values for these nodes in the middle are not observed. That is, you don't see what they should be in the training set. You see what the inputs are, you see what the outputs should be, but the things in the hidden layer are not seen in the training set. So that kind of explains the name hidden layer. It just means you don't see it in the training set. Let's introduce a bit more notation. Whereas previously we were using the vector x outputs X as well as the target outputs Y. So the term hidden layer refers to the fact that in the training set, the true values for these nodes in the middle are not observed. That is, you don't see what they should be in the training set. You see what the inputs are, you see what the output should be, but the things in the hidden layer are not seen in the training set. So that explains the name hidden layer. You don't see it in the training set. Let's introduce a bit more notation. Whereas previously we were using the vector x to denote the input features, an alternative notation for the values of the input features will be a superscript square bracket 0. And the term a also stands for activations, and it refers to the values that different layers of the neural network are passing on to the subsequent layers. So the input layer passes on the value x to the hidden layer. So we're going to call the activations of the input layer a superscript 0. The next layer, the hidden layer, will in turn generate some set of activations, which I'm going to write as a superscript. Subsequent layers. So the input A also stands for activations, and it refers to the values that different layers of the neural network are passing on to the subsequent layers. So the input layer passes on the value x to the hidden layer. So we're going to call that, use a bit more notation. Whereas previously we were using the vector x to denote the input features, an alternative notation for the values of the input features will be a superscript square bracket 0. And the term a also stands for activations, and refers to the values that different layers of the neural network are passing on to the subsequent layers. So the input layer passes on the value x to the hidden layer. So we're going to call that different layers of the neural network are passing on to the subsequent layers. So the input layer passes on the value x to the hidden layer. That different layers of the neural network are passing on to the subsequent layers. So the input layer passes on the value x to the hidden layer. So we're going to call the activations of the input layer a superscript 0. The next layer, the hidden layer, will in turn generate some set of activations, which I write as a superscript square bracket 1. So in particular, this first unit or this first node will generate the value a superscript square bracket 1 subscript 1. This second node will generate a value now with a subscript 2, and so on. And so a superscript square bracket 1, this is a four-dimensional vector, or if you want in Python, I guess it's purely a 4 by 1 matrix. Column vector, which looks like this, and it's four-dimensional because in this case we have four nodes or four units or four hidden units in this hidden layer. Then finally, the output layer will generate some value a2, which is just a real number, and so y hat is going to take on the value of A2. So this is analogous to how in logistic regression we have y hat equals A, and in logistic regression we only had that one output there, so we didn't use the superscript square brackets. For a neural network, we now going to use the superscript square bracket to explicitly indicate which layer it came from. One funny thing about notational conventions in neural networks is that this network that you see here is called a two-layer network. And the reason is that when we count layers in neural networks, we don't count the input layer. So the hidden layer is layer 1, and the output layer is layer 2. In our notational convention, we're calling the input layer layer 0. So technically, maybe there are 3 layers in this neural network, because there's the input layer, the hidden layer, and the output layer. But in conventional usage, if you read research papers and elsewhere in the course, you see people refer to this particular neural network as a two-layer neural network. So we don't count the input layer as an official layer. Finally, something that we'll get to later is that the hidden layer and the output layers will have parameters associated with it. So the hidden layer will have associated with it parameters W and V, and going to write superscript square bracket 1 to indicate that these are parameters associated with layer 1 with the hidden layer. We'll see later that W will be a 4 by 3 matrix and B will be a 4 by 1 vector in this example, where the first coordinate 4 comes from the fact that we have 4 nodes or 4 hidden units in the layer, and 3 comes from the fact that we have 3 input features. We'll talk later about the dimensions of these matrices, and it might make more sense at that time. But then similarly, the output layer has associated with it also parameters W, square bracket 2, and B, superscript square bracket 2, and it turns out the dimensions of these are 1 by 4 and 1 by 1. And these 1 by 4 is because the hidden layer has 4 hidden units, the output layer has just 1 unit. But again, we'll go over the dimensions of these matrices and vectors in a later video. So you've just seen what a two-layer neural network looks like. That is a neural network with one hidden layer. In the next video, let's go deeper into exactly what this neural network is computing. That is, how this neural network inputs X and goes all the way to computing its output Y hat. In the last video, you saw what a single hidden layer neural network looks like. In this video, let's go through the details of exactly how this neural network computes its outputs. What you see is that it's like logistic regression, but repeated a lot of times. Let's take a look. So this is what this neural network computes its. In the last video, you saw what a single hidden layer neural network looks like. In this video, let's go through the details of exactly how this neural network computes its outputs. What you see is that it's like logistic regression, but repeated a lot of times. Let's take a look. So this is what a two-layer neural network looks. Let's go more deeply into exactly what this neural network computes. Now, we've said before that logistic regression, the circle in logistic regression, really represents 2 steps of computation. First, you compute Z as follows, and then second, you compute the activation as a sigmoid function of Z. So a neural network just does this a lot more times. Let's start by focusing on just one of the nodes in the hidden layer. Let's look at the first node in the hidden layer. So I've grayed out the other nodes for now. So similar to logistic regression on the left, this node in the hidden layer does 2 steps of computation, right? The first step, think of as the left half of this node, it computes Z equals W transpose X plus B. And the notation we'll use is, these are all quantities associated with the first hidden layer. So that's why we'll have a bunch of square brackets there. And this is the first node in the hidden layer. So that's why we'll have a subscript 1 over there. So first it does that. And then the second step is it computes A11 equals sigmoid of Z11. Like so. So for both Z and A, the notational convention is that A, L, I, the L here in superscript square brackets refers to the layer number, and the I subscript here refers to the node in that layer. So the node we've been looking at is layer one. That is the hidden layer, node one. So that's why the superscript and subscripts were of 1, 1. So that little circle, that first node in the neural network represents carrying out these two steps of computation. Now let's look at the second node in the neural network, or the second node in the hidden layer of the neural network. Similar to the logistic regression unit on the left, this little circle represents two steps of computation. First step is to compute the C. This is still layer one, but now it's the second node equals W transpose X plus P to and then A on 2 equals sigma of C1, 2. Okay, feel free to pause the video if you want, but you can double check that the superscript and subscript notation is consistent with what we had written here above. talk through the first two hidden units in the neural network. Hidden units will also represent similar computations. So now let me take this pair of equations and this pair of equations and let's copy them to the next slide. So here's our neural network and here's the first and here's the second equations they were worked out previously for the first and the second hidden units. If you then go through and write out the corresponding equations for the third and fourth hidden units, you get the following. And so let's make sure this notation is clear. This is the vector W11. This is a vector transpose times x. Okay, so that's what the superscript T there represents. It's a vector transpose. Now, as you might have guessed, if you're actually implementing a neural network, doing this with a for loop seems really inefficient. So what we're going to do is take these four equations and vectorize. So we're going to start by showing how to compute C. Turns out you can do it as follows. Let me take these W's and stack them into a matrix. Then you have W11 transpose. So that's a row vector. It's column vector transpose gives you a row vector. Then W12 transpose, W13 transpose. And so this, by stacking these four W vectors together, you end up with a matrix. So another way to think of this is that we have four logistic regression units there, and each corresponding parameter vector W, and by stacking those four vectors together, you end up with this 4 by 3 matrix. So if you then take this matrix and multiply it by features x1, x2, x3, you end up with, by how matrix multiplication works, you end up with W1 1 transpose x, W1 W2 1 transpose x, W3 1 transpose x, W4 1 transpose x, and then let's not forget the b's. So we now add to this a vector b1 1, b1 2, b1 3, b1 4. So that's basically this. Then this is b1 1, b1 2, b1 3, b1 4. And so you see that each of the four rows of this outcome correspond exactly to each of these four rows, to each of these four quantities that we had above. So in other words, we've just shown that this thing is therefore equal to z11, z12, z13, z14, right, as defined here. And maybe not surprisingly, we're going to call this whole thing the vector z1, which is taken by stacking up these individuals of z's into a column vector. When we're vectorizing, one of the rules of thumb that help you navigate this is that when we have different nodes in a layer, we'll stack them vertically. So that's why when you had Z11 through Z14, those corresponded to four different nodes in the hidden layer. And so we stacked these four numbers vertically to form the vector Z1. And to use one more piece of notation, this 4 by 3 matrix here, which we obtained by stacking the lowercase, W11, W12, and so on, we're going to call this matrix W capital 1. And similarly, this vector we're going to call B superscript 1 square bracket. So this is a 4 by 1 vector. So now we've computed Z. Vector matrix notation. The last thing we need to do is also compute these values of A. And so probably won't surprise you to see that we're going to define A1 as just stacking together those activation values, A11 through A14. So just take these four values, stack them together in a vector called A1, and this is going to be sigmoid of Z1, where this now has been implementation of the sigmoid function that takes in the four elements of C and applies the sigmoid function element-wise to it. So just to recap, we figured out that Z1 is equal to W1 times the vector X plus the vector B1, and A1 is sigmoid times C1. Let's just copy this to the next slide. And what we see is that for the first layer of the neural network, given an input X, we have that C1 is equal to W1 times X plus B1, and A1 is So this 4 by 1 equals, this was a 4 by 3 matrix times a 3 by 1 vector plus a 4 by 1 vector b, and this is 4 by 1, same dimensions. And remember that we said x is equal to a0, right? Just like y hat is also equal to a2. So if you want, you can actually take this x and replace it a0, since a0 is, if you want, just an alias for the vector of input features x. Now, through a similar derivation, you can figure out that the representation for the next layer can also be written similarly, where what the output layer does is it has associated with it set of parameters w2 and b2. So w2 in this case is going to be a 1 by 4 matrix, and b2 is just a real number as 1 by 1. And so c2 is going to be a real number, right, as a 1 by 1 matrix. It's going to be a 1 by 4 thing times a was 4 by 1 plus b2 is 1 by 1. And so this gives you just a real number. And if you think of this loss output unit as just being analogous to logistic regression, which had parameters w and b, W really plays an analogous role to W2 transpose, so W2 is really W transpose, and B is equal to B2, right? So if we were to cover up the left of this network and ignore all that for now, then this is just, this last output unit is a lot like logistic regression, except that instead of writing the parameters as W and B, we're writing them as W2 and B2 with dimensions 1 by 4 and 1 by 1. So just to recap, for logistic regression, to implement the output or to implement prediction, you compute z equals w transpose x plus b, and a, or y hat, equals a, equals sigmoid of z. When you have a neural network with one hidden layer, what you need to implement to compute its output is just these four equations. You can think of this as a vectorized implementation of computing the output of first these four logistic regression units in the hidden layer. That's what this does. And then this logistic regression in the output layer, which is what this does. I hope this description made sense, but the takeaway is to compute the output of this neural network, all you need is those four lines of code. So now you've seen how, given a single input feature vector, you can, with four lines of code, compute the output of this neural network. Similar to what we did for logistic regression, we'll also want to vectorize across multiple training examples. And we'll see that by stacking up training examples in different columns in the matrix, with just slight modification to this, you also, similar to what you saw in logistic regression, be able to compute the output of this neural network, not just on one example at a time, but on your, say, your entire training set at a time. So let's see the details of that in the next video. Last video, you saw how to compute the prediction on a neural network given a single training example. In this video, you see how to vectorize across multiple training examples. Will be quite similar to what you saw for logistic regression, whereby stacking up different training examples in different columns of a matrix, you'll be able to take the equations you had from the previous video and with very low modification, change them to make the neural network compute the outputs on all the examples pretty much all at the same time. So let's see the details of how to do that. These were the four equations we had from the previous video of how you compute Z1, A1, Z2, and A2, and they tell you how, given an input feature vector x, you can use them to generate a2 equals y hat for a single training example. Now, if you have m training examples, you need to repeat this process for, say, the first training example, x superscript round brackets 1, to compute y hat 1. That's the prediction on your first training example. Then x2, use that to generate prediction y hat 2, and so on down to xm to generate a prediction y hat m. And so in order to write this in the activation function notation as well, I'm going to write this as a2 square bracket round bracket 1. This is a2, 2, and a2 m. So this notation, a square bracket 2 round bracket I, the round bracket I refers to or I, and the square bracket 2 refers to layer 2. Okay, so that's how the square bracket and the round bracket indices work. And so this suggests that if you have an unvectorized implementation and want to compute the predictions for all your training examples, you need to do for I equals 1 to m, then basically implement these four equations, right? You can see 1I equals W1 xi plus b1 a1I equals sigma c 1I c2I equals w2 a1I plus b2, and a2I equals c2I, right? So it's basically, these four equations on top and adding the superscript um, round bracket I to all the variables that depend on the training example. So adding the superscript round bracket I to x, c, and a if you want to compute all the outputs on your m training examples. What we'd like to do is vectorize this whole computation so as to get rid of this form. And by the way, in case it seems like I'm getting a lot of nitty-gritty algebra, it turns out that being able to implement this correctly is important in the deep learning era. And we actually chose the notation very carefully for this class to make these vectorization steps as easy as possible. So I hope that going through this nitty-gritty will actually help you to more quickly get correct implementations of these algorithms working. All right, so let me just copy this whole block of code to the next slide, and then we'll see how to vectorize this. So here's what we had from the previous slide with a for loop going over all m training examples. So recall Let's like give away the punchline and tell you what you need to implement in order to have a vectorized implementation of this folder. Turns out what you need to do is compute capital Z1 equals W1 X plus B1. Capital A1 equals sigmoid of Z1. Then capital Z2 equals W2 times A1 plus B2, and then A2 equals sigmoid of Z2. So if you want, the analogy is that we went from lowercase vector x's to just capital case X matrix by stacking up the lowercase x's in different columns. If you do the same thing for the z's, so for example, if you take z1 1, z1 2, and so on, and these are all column vectors up to z1m, right? So that's this first quantity, that all m of them, and stack them in columns, then this gives you the matrix C1. And similarly, if you look at, say, this quantity, take A1, 1, A1, 2, and so on, and A1M, and stack them up in columns, then this, just as we went from lowercase x to capital case X and lowercase z to capital case Z, this goes from the lowercase a, which are vectors, to this capital A1 that's over there. And similarly for Z2 and A2, right? They're also obtained by taking these vectors and stacking them horizontally, and taking these vectors and stacking them horizontally in order to get capital Z2 and capital A2. One other property of this notation that might help you to think about it is that these matrices, say Z and A, horizontally, we're going to index across training examples. So that's why the horizontal index corresponds to different training examples. And you sweep from left to right, you're scanning through the training set. And vertically, this vertical index corresponds to different nodes in the neural network. So, for example, value at the top leftmost corner of the matrix corresponds to the activation of the first hidden unit on the first training example. Um, one value down corresponds to the activation in the second hidden unit on the first training example, at the third hidden unit on the first training example, and so on. So as you scan down, this is you indexing to the hidden units number. Whereas if you move horizontally, then you're going from the first hidden unit, the first training example, to now the first hidden unit, second training example, the third training example, and so on until this node here corresponds to the activation of the first hidden unit in the final training example, in the M training example. Okay, so the horizontal, the matrix A goes over different training examples, and vertically, the different indices in the matrix A corresponds to different hidden units. And a similar intuition holds true for the matrix as well, as well as for X, where horizontally it corresponds to different training examples, and vertically it corresponds to different features, different input features, which are really different nodes at the input layer of the neural network. So with these equations, you now know how to implement a neural network with vectorization, that is vectorization across multiple examples. In the next video, I want to show you a bit more justification about why this is a correct implementation of this type of vectorization. It turns out the justification would be similar to what you have seen for logistic regression. Let's go on to the next video.
So I'm going to recap what I learned today. So for the first, what is the neural network? In logistic regression, we simply stack the input parameters to the one next step. Here, the input parameters as X, training example, and W and B, which is parameters, weight, and bias. But in neural network, as you can see, we stack a set of node for the next step, where we have a different weights and bias for each node. It is represented as a sequential order of equation in here, but there is another node in the neural network, but it is not represented in this image. So neural network representation base basically based on, based on this image. This is a neural network that has a one hidden layer. The A0, A superscript bracket 0 stands for the activation. This input layer passes on the value x to hidden layer. And A superscript 1 is first hidden layer in this case. And 2 for output layer. Just for reference, we don't count input layer uh, as a layer count in your network. So in this case, your network is called two-layered NN. In sigmoid function, in logistic regression, there's a middle step before the prediction stage. And the middle stage is composed of actually two separate stages, which is for the linear equation to solve what is the value of G and the activation function using sigmoid to get A. So in neural networks, we just follow these same steps to compute each of hidden node, but we use different bias and weights for each computations. So as you can see, the superscript is always same, regardless of the which nodes we are computing. Therefore, we are going to get four equations by following the same step for other nodes. As you can see here, we have same superscripts, but different nodes and weights. So instead of doing computations for these equations using a for loop in our program, it'd be better to use some kind of vectorization form as we already did in logistic regression. So if you're familiar to linear algebra, you might know that how to convert these four linear equation to matrix form, and it is represented as like this image, and we can just denote with it as a matrix with a large uh, capital alphabet, where G, W, B are matrices hold their components, and W matrix with a superscript 1 means that 4 by 3, yeah, 4 by 3 matrices, because X is a 3 by 1, 3 by 1 uh, column vector. So far, it is related to just one training example, but our goal is to compute every to get every prediction from M training examples, and we also need to vectorize these these equations by avoiding the for loop. And if we use the for loop, we're gonna follow these algorithms where I means that I is training example, and we can just vectorize it without by removing the I from the equations. And for example, the jet, the capital jet matrix with the superscript bracket 1 will be represented as these four because these i's components alive in the matrices, and horizontally is the training examples aligned, and vertically hidden unit aligned corresponding to the certain training example. So this is the end of this recording, today's recording. Thanks for your watching.